In last unit, we discussed the p-value. The concept is so important that we need to recall, review here. I get this from Wikipedia, and there are some others online discussion about the p-value. So first, the p-value is not the probability that the null hypothesis is true or the probability that the alternative hypothesis is false. It's not connected to either. We use our example to understand this. We know the p-value for our packing machine example is 4.56. And H0 is the mu equals 227. And HA is the mu is not equals 227. And this p-value equals 4.56%. We get these three numbers. Can we say that this one has 4.56% probability the population mean equals 227? Is this the meaning of p-value? H0 is this, and p-value equals 4%. Okay, we for short we said 4%, 4.5%. Is this the population mean equals 227 has a 4% of probability? This is true. Okay, not this is not. Or can we say that the population mean is not equals 227 has a probability of 4% of false? This one is also not true. The p-value is not the probability that our finding is merely a flunk. We said, okay, the probability, the population mean equals 227, but our sample equals 222. So here, for our finding, x bar equals 222. That you state your finding, this sample has a probability that is a mistake. That's 222 has a 4.5% probability. This is a mistake. That one is not true, because this sample is definitely correct, because this is a fact. You randomly choose that 4 boxes, you measure it, you calculate, that equals 222. That is a fact. It's not a mistake. We cannot say it's 4%, 4.5% that is mistake. That's not correct. The next one, p-value is not the probability of forcibly rejecting the null hypothesis. So here it said, we cannot accept that one. That means we said the mean of the population is not equals 227. That one will give us 4.5% of incorrect. This one statement is also not true. This p-value doesn't mean that if we reject this mu equals 227, you are going to have this chance of wrong. That one is not correct. So next, the p-value is not the probability that replicating the experiment would yield the same conclusion. Here, the first sample is the mean equals 227. You see that if you make another one, x bar 2, this one, what is the probability that this one still equals 222? We said, okay, that probability equals 4.56. Well, that conclusion is not correct. P-value doesn't mean the probability you repeat the experiment, the chance you get the same result. What is the chance you get the same result? We already know that, right? The chance you get the same result is 0%. The significant level, such as 5%, is not determined by the p-value. We calculate the p-value equals 4.56%. How do I know the significant level equals 5%? So once I get this p-value, can I choose 5%, or can I choose 10%, or can I choose 1%? Well, this significant level is not determined. It's independent of the p-value. No matter what your p-value is, this significant level, either equals 5%, 10%, or 1%, has no relationship with this p-value. It's a totally different thing. So next, the p-value does not indicate the size or importance of the observed effect. What does that mean? In our example here, the p-value equals 4.5% is less than the significant level of 5%. So our conclusion is we reject the hypothesis H0, means we need to recalibrate the calibrating machine, revise the calibrating machine. How serious is this? We don't know that. You cannot conclude the seriousness or the importance of this effect from this p-value. The p-value is 4%, 5%, or 1%. We cannot. The statement is we need to reject the H0, but we don't know how important or how serious that is. The concept of p-value is far from perfect. This is only one concept. On website, there's a lot of other discussions about p-value. Actually, there are a lot of research papers discussing this p-value. There's even a video on YouTube listed a lot of examples in the scientific area that some research teams manipulate this p-value or something, so make a lot of mistakes. So p-value is far from perfect. This is only one method. When we calculate the p-value, we compare that p-value with the significant level alpha. In our example, we choose alpha equals 5%, and that choice of 5% is independent of the p-value. So significant level alpha is the largest p-value tolerated for rejecting a true null hypothesis. How much evidence against H0 we require? So how did they decide a significant level alpha? This alpha is the largest p-value that we need to reject the H0. This value, the significant level alpha, is decided arbitrarily before conducting the test. If the p-value is equal to or less than this, then we reject H0. If the p-value is greater than this, then we fail to reject this. For example, if you are required to do an experiment, before you even conduct the experiment, let alone you calculate the p-value, you don't even know that. Even before you do the experiment, you need to decide what significant level alpha you want to choose. You want to choose 1%, 5%, or 10%. Once you decided this p-value, this significant level alpha, then you conduct the experiment, you calculate the p-value, you compare your p-value with alpha, and get the conclusion. In our example, again here, does the packaging machine need revision? Before you do this example, we set the alpha equals significant level equals 5%. Then your conclusion will be, because your p-value equals 4.56% and less than this, so we state that is significant, so we reject H0. How about before you do this experiment, I choose this one to 1%. Alpha equals 1%. Then for the same experiment, you'll get the same p-value, 4.56. And this one is greater than the significant level alpha. That means this is not significant. That means we do not need to recalibrate the machine. That is possible. So you can see from here, the p-value concept is important, but p-value alone cannot decide your conclusion about H0. You need to compare it with a predefined significant level R. When the z-score falls within the rejection region, the shaded area on the tail side, if the z-score is in this side or the z-score is on this and here, the p-value is smaller than the alpha. Where is alpha? Alpha is in the middle. So this is alpha. This is alpha. This is alpha. The alpha value here is for alpha equals 1%, means this area equals 1%. This one equals one-sided test. So this one area equals 5%. So this alpha equals 5%. And this two-sided, alpha equals 1%, then this side equals 0.005. This side is also equals 0.005. If your z-score falls in this rejection region, this side, or this side, or this side, then your p-value is smaller than alpha, and we have statistical significance. Rejection region for a two-tail test of mu with alpha equals 5%. 5% means the rejection area equals 0.05. And because this is a two-tail test, so each side, this value must be equals, this area must be equals 0.025. This also equals 0.025. And when we use table C to determine the Z star, we cannot use 5%. Although this here equals 5%, but we need to use a half of this one for two-tail test. So corresponding to this equals 0.025, not this one. This one is wrong. We need to use this. So this one corresponding to significant level equals 95%. And this Z star equals 1.96. How to memorize all this? We just use this normal distribution diagram. So we can easily get this result from one-sided or two-sided. Okay, we discussed the confidence level before, and in this unit we discussed to test the hypothesis. Those are the two methods of inferring for a parameter for the population. So what is there any relationship between these two? A two-sided test is symmetrical. We can also use the confidence interval to test a two-sided hypothesis. That means, yes, they are related. In a two-sided test, this probability is C, confidence level C, and this part will be equal to the significant level alpha. So C plus alpha will be equal to 1. C is in the middle. Alpha is this and this. This is two-sided test. Then alpha equals 1 minus C equals this. Then for this area will be only 1 minus C then over 2. This also equals 1 minus C over 2. So in our example here, the packs of cherry tomatoes, we know the population standard deviation equals 5 grams. And our mu equals H0, in the H0 equals 227. the HA is mu is not equal to 227. Then based on what we learned in the previous unit, we can calculate the confidence interval for 95%. 95%, then mu equals, we said this is x bar plus minus z star, and z star is here, then times standard deviation over square root of n, and this one, for 95% confidence, z star equals 1.96. and sigma equals 5, n equals 4. We plug in the numbers, that equals 222 plus minus 4.9, which gives us this end and this end, 217.1 and 226.9. Look at the H0. We want to test is mu equals 227. 227 is outside this confidence interval. So our conclusion is we reject H0. So this is the relationship between the confidence intervals and the test hypothesis. So they are related. Next, we further discuss the meaning or the logic of confidence interval test. A confidence interval gives a black and white answer, yes or no, and we reject or don't reject H0. But it also estimates the range of likely value. In our example here, the confidence letter will estimate the mean of the population is between 217.1 to 226.9. And for significant testing, we don't know this information. We only said we reject or we fail to reject. For confidence level, in confidence interval, we have this extra information here. A p-value quantifies how strong the evidence is against the H0. How strong the evidence is against this H0 based on the p-value. And the confidence interval give us a range somewhere to somewhere, but we don't know how strong the evidence is. This one we know how strong the evidence is, but we don't know the interval. That means we lack this information about the estimation of the mean. We only say we strongly, the evidence is strong, so we reject the H0 or we fail to reject H0, but we don't know, we have no estimation about the population mean here. And for confidence interval, we are given an estimate of the range of the population mean, but we don't know how strong the evidence is. So we can see these two confidence intervals and p-values focus on different characteristics. But they are, in some sense, are related. Here we have an example. A sample gives a 99% confidence interval of as this. X bar is the mean of the sample plus minus, this is called the margin of error, right? And this mean equals 0.84 plus minus 0.0101. And we know the confidence level equals 99%. Now we want to know, could this sample, this random sample, be from a population whose mu equals 0.86? For this confidence interval, we draw this. The sample mean equals 0.84. So this one is here. And plus minus 0.01. So it's from here and here. So this is this part and up to this part. This is the confidence interval. Can this sample, random sample, come from a population whose mu equals 0.86? We said no. We reject this H0. So it's not possible from a population of 0.86. How about mu equals 0.85? 0.85 is here, is within the confidence interval. So that is yes. As we said, the significant alpha is not from the p-value. Right? And this, the choosing of a significant level alpha will affect your conclusion. Because the p-value is calculated, then you compare with the significant level alpha. So how to choose the significant level alpha? We have several factors to consider. The first one, what are the consequences of rejecting the null hypothesis? For example, if you want to study about the global warming, and in this case, if you reject a null hypothesis, what will be the consequence? The consequence will be not that serious. Global warming or not, it is important, but it's not that serious. So you choose a significant level alpha is large, for example 5%, that is okay. It's 10%, fine. 20%, that is no big deal. But if you want to use this significance testing to convict a person for life with DNA evidence, how are you going to choose the significant level alpha? Because this thing here is very serious. You'd better choose alpha small. So in this case, you want this significant level alpha, for example, equals 1% or even more, even less, 0.1% or maybe even smaller, because this is very important. This is the first point. The second point, are you conducting a preliminary study? For example, you try to invent a drug that can cure the cancer, and you get some result, experiment, you get a result. In this case, you do not want to miss any interesting result. The drug you invented may be effective to cure a cancer. But sometimes if you choose the significant level too small, then you said that result is not significant. Then you just reject your H0. So that is not a good idea. So for preliminary study, the effect may be significant, so you want to choose a significant level as large. For example, you choose 5% or 10% or larger. But for this one here, you want to choose a smaller, maybe even smaller. So that's really the choice of a significant level alpha really depends on what we are doing. Some conventions, if you don't want to choose by yourself, we typically use the standard of our field for work. As far as I know, most will choose 5%. Another thing to consider is there's no sharp cutoffs. You said we choose 5%. How about I choose 4.9%? How about I choose 5.1%? In our packing example, the p-value equals 4.56%. You can choose 4.5%, or you can choose 4.6%. These two will give a totally different conclusion. So what's the point you choose 4.5 or 4.6, right? This one is not that important. The important thing is the magnitude of the p-value. Somewhat significant or very significant. But the choice of a significant level alpha, we don't need to be has sharp cutoff. We can just use 5% or 1%. the significance is from the p-value. Another point to consider is practical significance. We just discussed the statistical significance. These two are different things. Statistical significance only says whether the effect observed is likely to be due to chance alone because of random sampling. Even this is statistically significant, it may not necessarily practically significant. Or, on the contrary, even this is not statistically significant, doesn't mean it has no practical significance. Statistical significance may not be practically important. That is because statistical significance does not tell you about the magnitude of the effect, only that there is one. An effect could be too small to be relevant, and with a large enough sample size, significance can be reached even for tiniest effect. Okay, we have an example here. A drug to lower temperature is found to reproducibly lower patient temperature by 0.4 degrees Celsius. And with a p-value of 1%. So this is very significant. For a p-value is less than 0.01. But that effect is only 0.4 degrees reduction. So in practice, clinical benefit of temperature reduction only appears for at least 1 degree decrease or even larger. So this 0.4 is statistically significant with a p-value of 0.1%, but actually is not practical significance. It's not almost useless because only reduced by 1 degree or larger, this has meaningful in practice. So that means if your result is statistically significant, not necessarily mean it's practically significant. On the contrary, if you cannot find significance statistically, that doesn't mean it is practically not significant. Failing to find statistical significance in a result is not rejecting the null hypothesis. We said if this is significant, means the p-value is small, then we reject because that is p-value is small. That means this is significant. So we are going to reject. But if you cannot find a small p-value, that means it's not significant, then we are not saying we do not reject this hypothesis, null hypothesis. This is very different from actually accepting it. Now, we failed to reject doesn't mean we accepted it. The sample size, for instance, could be too small to overcome large variability in the population. Another example is when we compare two populations, the lack of significance does not imply that the two samples come from the same population. They could represent two very distinct populations with similar mathematical properties. We have examples in British Medical Journal. There's one, its title says, "Absence of evidence is not evidence of absence." Second is, having no proof of who committed a murder does not imply that the murder was not committed. Okay, the next is interpreting effect size. It is all about context. There's no consensus on how big an effect has to be in order to be considered meaningful. In some cases, effect that may appear to be trivial can be very important. For example, improving the format of a computerized test reduces the average response time by only 2 seconds. Right? By only 2 seconds. Although this effect is very small, it is important since this is done millions of times a year. So the accumulative time savings of using the better format is gigantic. It's very large. Right? You always think about the context. Try to plot your result and compare them with a baseline or result from similar studies.